Where was I? InnoQ, Jan Stępień. That's me. I'm very happy to be here with you today. Always a pleasure. Allow me to start with a short story. Not long ago, I was in London. I was booking my tickets, and the airline, I'm not going to name the name of the airline, asked me to provide my surname exactly as it appears in my passport. So I looked at my passport, and I thought, what can potentially go wrong? Well, this is the confirmation email I got from them. So notice two interesting things. Firstly, my surname is mangled in an interesting way because one character is simplified to 7-bit, and the second one is removed altogether. And the German one, Bestätigung, which stands for confirmation, is botched in two distinct ways. Firstly in the header and then in the body of the message. So why am I sharing this story? Because I think that writing correct software is really hard, and I think we can all agree on that, right? We're really bad at writing code. There are methods we typically apply and given this difficulty. Some of them were discussed by Chus earlier today, for example, using more advanced, more expressive type systems. But what I'm going to talk about today is tests. Usually, we write tests to address this difficulty somehow. In the Clojure world, which I intend to focus on today, we typically start with an empty skeleton of a project, which by default comes with a single test, is broken, and we have to fix it. This is a good starting point. We use testing, we write tests at a variety of levels. We write integration tests, unit tests, acceptance tests, user interface tests. We even use more advanced techniques like generative testing, which is taking the Clojure community by storm, where we can express more general claims about our software and then use the library to have our claims subjected to an entire hail of inputs and test our understanding of a domain far better. Like here, for example, checking whether stored is idempotent. But this is not enough. And it's not enough because it's still writing tests. And as we already know, we're terrible at writing code, right? So why would we be any better at writing tests? There's a number of methods, techniques, which try to help us somehow to increase our, the degree of our trust to our test suite. Some of them are, for example, code coverage techniques. They're insufficient in many cases. Today I'd like to focus on something else. Today I'd like to focus on mutation testing. Oh, I missed this slide, sorry. Because I was intending to tell you, now I blew the joke. I was intending to tell you that we're, all in all, we're writing tests. And we can't tell for sure how was the quality of our tests, because there is no one behind the scenes who is testing our tests. And mutation testing is a technique which allows us to firstly evaluate the quality of our test suite, as well as give us concrete hints how to improve it. Mutation testing was already briefly discussed during a very interesting lightning talk yesterday evening. Today I'd like to start with giving you some theoretical background to this technique. It all starts with the competent programmer hypothesis. According to it, code written by competent programmers, you, differs from correct code only by a small number of faults we accidentally introduced into our code. Thus, a good test suite will help us eliminate those few faults we accidentally put there. So how can we tell whether a test suite is any good? Well, we can just grab the keyboard and introduce a couple of faults and check whether the test suite catches them or not. If the test suite turns red, it's a good sign. As we all know, we barely have time to write correct code. So on top of that, trying to check our test suite by writing incorrect code seems like not an economically viable method. What we do when we don't have time for things, we try to automate them. And this is what we can do. We can try to automatically generate faulty versions of our programs and subject them to our test suites and see whether our tests turn red when they see them. If they do, excellent. If they don't, there is a problem. But now you might ask, and rightly so, but there are so many ways we can introduce bugs and faults into our programs. And if you take combinations of those simple faults we introduce, there's a combinatorial explosions of possibilities. This brings us to the second hypothesis, the coupling effect hypothesis. According to it, a test suite which would discover simple faults will also discover more complex faults which are combinations of those simple ones. Thus, complex faults are coupled to simple ones through the test suite which would discover both of them. And those two methods offer us a foundation, a theoretical foundation for mutation testing. That is, we generate faulty versions of our programs, run our test suites, and if those test suites remain green, we know there is something we missed in our tests. Let's get some concrete vocabulary defined. Those invalid versions of our programs we generate are mutants. We try to kill those mutants using our test suites. If a test suite turns red, the mutant is dead. Those which still remain alive after the run of our tests are called survivors. Mutation testing, like many good things in computer science, is several decades old. It was introduced in the beginning of 1970s and was subject to, according to this very interesting review paper, was subject of over 400 scientific publications. 400, yes. According to existing research, both the coupling effect and competent programmer hypothesis are confirmed, thus giving backing to the entire method. Existing research focused on languages which were mainstream over those decades, so primarily C, Java, and Fortran. But still, there's a lot of interesting things happening right now. There are very interesting and powerful implementations of this technique for languages like Ruby, Java, JavaScript. I recommend taking a look. What brought me to this subject was the fact that I wasn't able to find a mutation testing library for Clojure. So I decided to write one, and here on a couple of following slides, I'd like to tell you something about Mutant, my mutation testing library for Clojure. The library itself is executing four simple steps. It reads all sources in a directory you pointed to, in your sources directory. Then, for every single top-level form in your sources directory, it tries to generate mutated variants of this form. It runs test suite, which it finds in your test directory, for every mutant it generates. And then it reports all the survivors. All the survivors, it is all those mutated variants of your Clojure code which didn't cause your test suite to turn red. Let's talk about those steps in a bit more detail. Firstly, we have to generate mutants. Clojure, a homoiconic language, comes with excellent tooling for manipulating its source code. A library which I found very useful is rewrite-clj. Does anybody know rewrite-clj? Does anybody know lane ancient? Bit more hands. It's a very nice line-in plugin which allows you to automatically get upgraded versions of dependencies in your project CLJ file. It builds upon rewrite-clj, which is a tool for manipulating your Clojure files, preserving indentation, white spaces, comments, and all this noise. I'm using this library to process our Clojure files and generate some invalid variations of your code. For example, if I run into an AND expression in your code, I might turn it into an OR. If I see less than check, I might turn it into a less or equal. Given the empty predicate, I might try to turn it into a seek, which is a negation in a Boolean context. And then finally, given some function of arbitrary complexity, I might just remove this body altogether. Super efficient, I tell you. Many tests will pass. Anyways.
It's an ultimate refactoring.
Absolutely. Automated refactoring. So what we have are those modified versions of our program. Now we have to reload the code. In Clojure, we have solid foundations, right? We can dynamically reevaluate functions. We can even add and remove namespaces however we will. This is very helpful. But reloading just this one function is not enough, right? Because the function itself might have affected everything what's in the same file below it and all the other files which are requiring this particular file. A tool which comes very useful is Clojure Tools namespace, which comes with a number of useful namespace mangling processing functions. One of them allows me to build an entire graph of dependencies of those require statements in your Clojure projects. This allows me to reload all potentially affected source code, which might be too much to recompile, but I haven't yet found any better way to attack the problem. And at this point, I know that your code is mutated. All the affected code is also updated, and I can proceed to running the tests. Running tests is just looking at your test namespace you pointed me to, invoking Clojure core test to run tests on it, and collecting results. If your test suite turns red, I just move on. If your test suite remains green, I preserve the mutant and finally demonstrate in a single report. Here, for example, is a report of mutant running on itself. It's an extract from this report. It took a bit of hacking to get the thing run on itself, but it works. And here it reports that it found 8 survivors, and here I'm showing 2 of those. You can see that if I replace this end with an or just remove the entire body of this function, all the tests are green because I'm horrible at writing tests. And I'm very happy because this thing works, right? This thing, I ran it on a number of prominent Clojure open source projects and was able to generate actual survivors which are not caught by those projects. I'm not going to name any names because that's not the point. The point is this thing works. This thing is in a state where we can start applying it in our code bases. This being said, it's too early to get excited about it. There are still a number of rough edges which I'd like to discuss here. First of all, it's slow. It's forbiddingly slow. Authors of a paper from 2001 discussed 3 main solutions to the problem of high CPU cost of mutation testing. Smarter, faster, and fewer. Fewer, faster, and smarter. Let's talk about those 3 approaches one after another. By fewer, we are talking about generating fewer mutants. We can select what to mutate. Maybe we don't need to mutate every single form because the chance that it will yield survivors is relatively low or next to 0. We will return to this topic in a couple of minutes. We might select our mutation operators, that is the way we generate mutants. Maybe some mutants are very unlikely to generate survivors. So running tests on them is a waste of time anyway. We might also sample mutants. According to some research, randomly sampling just 10% of mutants you generate and subjecting them to your test suits allows you to, rather yields 80% of survivors, meaning you do 10% of the work and get 80% of the result. It might be a trade-off you're interested in. Let's talk about faster. One of the things which you can do, and I introduced in the library which I wrote, is not restarting the VM. Keeping the JVM hot and reloading the code directly in it. If your virtual machine supports it, Beam, the Ruby virtual machine, or any other VM which allows live code reloading, this is a method which will allow you to speed up the process significantly. Another approach, especially in the advent of cloud computing, is just throwing machines at the problem. Notice that once we generate mutated versions of our software, we can just scatter them across our machines, which will independently run the test suite and report back whether it was green or not. the problem is pleasantly parallelizable. Of course, the trickiest bit is to think it's smarter. But it's still worth taking a look at. We might execute only relevant tests. That is, follow this dependency graph of our namespaces and try to run only tests which actually have a chance of killing the mutant. If we modified something in the somewhere in the view logic, it's unlikely that the database tests will catch it, right? So it's not worth to execute them, it's just a waste of our time. We might also reorder the test suite. This is an idea which I find interesting. We might notice that certain tests are more likely to kill mutants than the others. Now, if we're able to notice the fact that when we're running a test suite, we can stop running the test suite after the first red test because we already know that the mutant is dead. Which means that if we reorder our test suite and put all the tests likely to kill mutants at the front, statistically we might save some time because less relevant tests will be run towards the end. All what I discussed is still nothing compared to the fact that the whole thing might not terminate, which I find delightful. If you generate a mutant which has an endless loop inside, which I did a number of times, you end up with this really unpleasant situation, and the underlying platform does not help. First of all, JVM cannot reliably stop threads. There is a method called thread interrupt, which is just a polite, excuse me, could you stop? You can ignore it. There is thread stop function, a method, which is deprecated, and there is a lengthy explanation why you shouldn't use it, mostly because of portability reasons and lack of predictability of this method. You might want to fork out, create a sub-process on the Unix system and run your tests there, and then if the thing runs for too long, just kill it. You can't do that because JVM, for portability reasons, does not implement the POSIX fork syscall. Well, you might want to start one JVM per a test suite, but this is, again, even more costly, even more expensive. In other words, I don't have a solution for this problem. So if you have an idea, let me know, because I want to hear from you, right? This is something which other mutation testing libraries can solve by, for example, forking out and killing their sub-process. I can do it in JVM. After all what we've discussed so far, I think it's worth to mention which path to introducing mutation testing might be might return best return on investment. This is an idea which we came up with. I mean, it wasn't our idea. It just appeared in a discussion, and it turned out that a lot of people were thinking about it at the same time somewhere completely else on the globe. An idea of running your mutation tests and a continuous integration, continuous delivery pipelines. Notice that given the high cost and high CPU cost, the time it takes to run mutation tests, it's not really possible to convince your fellow developers to execute mutation testing in their TDD cycles. It just takes way too long time. It's also unlikely that you will convince them to run their mutation testing analysis right before they push to either master or a feature branch. So why not try to automate it again, like we did at the beginning of the talk? Why not let our continuous delivery pipelines run all those mutation tests for us, and then as you're about to create a pull request to the master branch from the feature branch you're working on, you get back a feedback, one from a traditional CI system telling you, yes, all tests are green, that's cool, and then a follow-up one saying, all tests are green, but still there are certain cases which you haven't covered. I mutated your code somehow, and it resulted in uncaught problems, uncaught potential regressions. Notice that there is one more thing. If we introduce this method in our mutation, in our continuous delivery pipelines, we have full historical knowledge of what was just modified. Meaning, looking at lines which were just touched in the previous commit, we can narrow the scope of our mutation analysis just to stuff which was modified. There is no need to run a mutation analysis on the entire project. We just focus on the code modified with your current commit. Maybe not just those lines, but maybe entire functions, entire classes, files. This allows you to introduce mutation testing where it's most valuable, on the code which is just modified, on the code which is hot and valuable right now from the perspective of your business, of your organization. And additionally, putting it there allows you to introduce the whole method gradually, because you're not breaking anybody's workflow. You're not forcing people to run the thing on their machines, which will likely meet some opposition. As long as you put it on some server which will periodically pull your stuff from your Git repository, you can slowly and painlessly introduce mutation testing into your organization and see how it performs, how it helps you write better software, or more importantly, better tests for your software, because that's the whole point. It might appear that I'm so far like waving my hands in the air talking about this entire continuous delivery pipeline thing, but there are concrete case studies. 2 years ago, an engineer at InView, sorry for mispronouncing, Llorenç Martí García, wrote a very interesting blog post. At InView, they were dealing with 100,000 lines of a C++ 3D rendering engine, a complex and mature beast. They were happy with their tests and the pace of their development, but they noticed that they were slowing down. And they, according to their analysis, the fault was the fact that the quality of the test suite deteriorated, and this prevented them from moving as quickly as they were moving before. They were looking for solutions. They looked at code coverage as a simple approach to the solution to the problem. It didn't work for them. So they decided to just randomly remove lines from their C++ code base and see whether the test suite breaks or not. Exactly what mutation testing is about. And they introduced it as part of their continuous delivery pipeline. They worked on small C++ commits, mutated only things which were touched by those commits, and got actionable results, actionable feedback related just to the code which was hot right now from the perspective of the business. Either add more tests here because something is missing, or just throw it away because it's dead code. And they didn't need to introduce this method on the scale of the entire 100,000 lines of C++ engine. They could have introduced it gradually, commit by commit, only on the code which was important right now. And their feedback was excellent. They were very happy with results of the method, of the feedback they got from the method. And it's an excellent confirmation of how mutation testing can be introduced in a mature organization dealing with a massive code base in a language which you wouldn't expect to fit to this method nicely. I hope that in this short talk, I was able to convince you that mutation testing is a viable method of evaluating the quality of our test suites, as well as increasing this quality. Tools are there, they're available. For most programming languages we typically work with. Some of them require some further work. For example, non-termination becomes an issue. But they are there, right? Now the topic is, how do we introduce them into our code bases? Be it your Java code base, be it your Ruby, Scala, JavaScript, or any other code base, or Erlang, as we saw yesterday. I think that mixing existing tooling with putting it into our continuous delivery pipelines, we've got a very natural way of introducing this otherwise, well, earthquakey method into our quality assurance pipelines, if you like. This is all I've prepared, so I would like to thank you for your attention. You've been a great audience, and I think I'll open the floor to your questions. Thank you all very much.
Hi. While testing popular libraries, weren't you scared that your functions became impure and delete, for example, your entire disk?
This is a very good comment. Yes. What if? Another reason for doing it in your continuous delivery pipeline, right? But this is possible. Mutations I'm introducing seem to be relatively simple things. There is a lot of existing research about what mutations you introduce to your software, like what's the yield of particular mutations, how effective they are. And they are typically very simple things, right? Simple mutations, testing your edge cases, testing your Boolean conditions and so on, arithmetic, off by one things. Yeah,
but does this software that you download from open source and then mutate, they could have something which, if condition changes, some impurity, some, I don't know, file access, which is normally not executed.
Suddenly, yeah, if true, remove everything, and then I accidentally invoke this true, and it removes everything. Yes, run it in Docker containers. Thank you. It's a very good comment. Thank you very much for this. I don't have a good answer.
Or is there also libraries that protect against?
Sorry, I think I have a question coming there.
You didn't say anything about equivalent mutants in your talk. How big a problem have you found those to be?
Excuse me, equivalent?
Equivalent mutants which still work because they are equivalent to the original program.
Thank you very much for this question. Yes, this is an excellent comment. What if, for example, I will remove a log statement from your code as part of my mutation, right? Your test suite remains green, but, well, it's kind of a mutant, but it just was a mutant saying log.debug something, so it technically doesn't break anything, right? How do you address this problem? I don't know. I think it's a very good point, and maybe some form of blacklisting mutants which shouldn't be generated, or ones which I don't care about. I have to look into it. I'm sure that people studied the problem, and I think I just need to dig into what they found out. Thank you for this question.
What's the how useful do you think mutation testing is in projects where there's not 100% coverage, or the tests are failing depending on the order you run them in? So, is this something that you would introduce only in a very mature, very stable test suite, or do you think it's useful in any kind of project?
Yeah, I understand you're referring to the so-called real world, right? It's dangerous there, yeah. So, sure, if you don't have any kind of normal line coverage of your code with your test suite, then introducing mutation testing seems like quite a big artillery for a problem which you could solve just by writing simple unit tests, right? So it's a bit too early to introduce mutation testing there. I think that this tool would, in the real world, excel at either code bases which are already well tested, but you want to increase your trust in your test suite to be in its likelihood to catch regressions in the future, or focusing it on your most important and bug-prone things, either bug-prone things or things which are where a cost of a potential regression will be very high, like your actual internals of your business logic. If you can extract the logic of your organization to some modules, which are otherwise decoupled from the rest of the world, from the I/O, and just focus your mutation analysis just on this thing, then you might introduce mutation testing partially where it's most needed, because costs of introducing faults there will be the highest. I hope this works as an answer or a comment.
So as a follow-up, so if you had to choose between this and property-based testing for that sensitive area of your code, which would you choose if you had to choose one, like allocate your time only for one?
I'm a great fan of property-based testing, by all means. This being said, mutation testing addresses a different problem. Mutation testing, for my understanding of the term, property-based testing helps us write better tests, or rather, we write better tests using property-based testing. And then mutation testing is something watching the watchers. It tells us that those are really nice tests, but they still haven't covered the following things. So they're not solving the same problem. One is helping another. I think we have a question here in the front. The microphone is coming.
Yes, it is.
I think because we're recording all of those questions, right?
So idea from property-based testing also, do you somehow shrink mutators if you mutate in several places?
Good question. I'm already generating very small mutations. So if I'm flipping less than to less than equal, there is not much I can shrink anymore.
Okay.
Maybe there are ways where you can, I removed the entire body of the function. This surely can be shrunk to removing subforms or something inside, absolutely. But in some cases, some mutations are relatively tiny, so reducing them even further, I would find it difficult.
Okay, thank you.
Oh, we have three more questions. I'm so happy because I think we still have time for them.
Have you thought about implementing a feedback loop? I mean, when you get the results from your mutations, and it's really something that you should look at, and then based on that information, you could instead of doing it only by some template, you could learn the mechanism, and based on feedback that you get from, you can improve it on the next level.
I haven't considered that, but it sounds very interesting, and let's talk about it afterwards. It sounds very cool. I saw two more hands at least, and there are no bad questions. Remember, there are only bad answers.
My question is, when you create mutants, do they actually usually have only one mutation, or do you prefer to create mutants with more mutations at once?
I generate just single mutation and test your code on a single mutation, and I would assume that this is the right way to do it based on the coupling effect hypothesis. That is, the assumption that if my test suite catches a fault based on one mutant, it will also catch one which has two faults inside of it. Also, there is a chance that two mutations I would introduce at the same time will cancel each other out. And then I have the situation of, this is kind of bad, but also it's totally fine.
Mm-hmm. And my second question, regarding the mutation possibilities, do you take inspirations from other software only, or are there mutations that you actually, let's say, invented by yourself?
No, I claim no novelty here. I'm heavily inspired by all the existing work which has been happening. All I did is I would just keep adding parentheses and running it to JVM.
Okay, thank you.
Have you done any work on parallelization of mutant? I mean, to make it practically runnable on multiple nodes?
I haven't. This is something which is on my to-do list, but I haven't yet invested any time into it.
Thank you for your talk. To me, it looks like the mutants testing is sort of extending of the coverage. So if you actually get information from some sort of coverage utility, which tells you, look, this function is not used, or this branch of the if condition is not used, you can actually skip those mutations because they are useless. So if you would actually hook your tool to a coverage tool, getting information from the paths that are not executed, you can actually save in mutations.
Mm-hmm. This sounds very interesting. I haven't thought of that. Let's talk about it.
Sure. I have other couple of things, but
excellent. This sounds great. Oh, come on. There must be at least one more question. We still have time for it, I hope. Oh, sure we do.
Thank you for the talk. Actually, about the question of shrinking, do you think it was more reasonable to expand mutations? Because it's kind of complementary to property-based testing. You don't want to have the smallest mutation. You actually want to have the largest mutation, which is still goes unnoticed by the tests.
How much of your code can I delete before your test use catches it?
Yeah. So how
I like the idea. Joke aside, I like the idea. I would still have to wrap my head around it, but this sounds like a really cool thing. And instead of shrinking mutants, we can just keep growing them. Sorry, you were intending to say?
No, I just want to say I think it's different because I do understand your argumentation about if the test suite cannot catch a small catches a small error, it will probably catch a bigger one. Mm-hmm. But these are the big ones we're going after, and maybe expanding would be a good idea.
It's a very good thought. I'm wondering how it fits into the competent programmer hypothesis. That is the assumption that your code was generally correct, give or take a couple of small things you forgot about. And mutation testing focuses on catching your small edge cases. And like, unlike my test, which you saw, if you delete the entire function and the whole thing still works, I mean, tests are green. In the case of like well-tested projects or well-implemented projects, this should not be the case. But still, thank you. A very interesting thought.
What is the technical way of introducing the mutants? I mean, is it just a simple text substitution, or is it more sophisticated? Some, I don't know, parsing, etc.
Very good question. The way I'm doing it is using rewrite CLJ. I can read code from disk and get it as a string. Wait, that's before rewrite CLJ. Then I get the string. I run rewrite CLJ on my string. I get a zipper-like representation of my code base. It's a data structure allowing you to a degree, easily process your code, process your data structures. This allows me to change something in this like AST-like data structure. Then I can get back from the zipper representation using rewrite CLJ API. I can get back a proper Clojure data structure, which is like your code but with default, and then I just eval it. And then I proceed to evaluating all the rest of your forms unchanged. Thank you, very good question.
Yes, so this would be the follow-up of this question. So wouldn't it be better to do this on bytecode level rather than on source code?
A very good point. This is how the Java library does it. The Java library, PIT test, is executing on the bytecode level. It takes your class files and does some mutation of the bytecode which would correspond cleanly to some changes in your source code. And if this fails, it's able to like re-render what it did to the bytecode and show it how it would look like if you did it in your source code. Whether I can do it in Clojure, probably yes. Whether I know enough about JVM bytecode, sure not. So it's something which is a matter for.
I don't think it's going to be that easy because you can't predict actually what bytecode will be rendered from your from a Clojure code.
Probably faster and way more difficult. Do we have time for any more questions?
I think we'll have time for one. So how many, if any, of these kind of survivors can be considered kind of false positives? Things that are actually fine with your test and the survivor just tells you there's a problem but maybe there isn't.
I think what your question is closely connected to what we've heard at the very beginning of the Q&A session, that is those mutants which are equivalent because I just removed the log statement from your code and everything still works, right? False positives, how many of them? It's difficult to say. I think it depends on mutation operations which the library offers, on your code, at any rate, whatever is their source and how many of them are there, some method must exist to address the problem of those mutations. Maybe some regular expression like syntax which allows you to say, if in your mutant debug appears, ignore this survivor because I don't care anyway, or something. I'm sure there is a research going into this topic which I haven't touched on. Well, I guess this was the last question. So thank you all very much for being here with me today. And if there's anything more, I will be there with you drinking coffee. Thank you very much.
Thank you.